have a look at the PowerPoint and do some of the problems in there. So again, the it's from the other one. So again, we're looking at the chain rule. So this is taking the derivative of composed functions, meaning one function is essentially plugged into another one. So something like f of g of x that you'd see right there. You could also do it the other way, g of f of x or anything like that. So again, I normally think of it with the prime notation in terms of number one. So if you have capital F of x is f of g of x, then the way you take the derivative is f prime of g of x times g prime of x. So usually the way I write it is I'll think of an inside function and an outside function. And then I'll set it up that way. They also have the one using the Leibniz notation at the bottom, where if you think of y as f of u and u is g of x, then the way you do dy of x is dy du times du dx. But usually it's not quite as simple to write it down that way. Sometimes Leibniz notation is definitely the better way to think about things. If we had several variables, it might make more sense. So, definitely in multivariable functions, the Leibniz notation is preferable. But here in single variable calculus, it's usually just easier to think about in terms of that rule number one. But if you have a different way you like to set it up, that's fine, as long as you're getting to the same solution at the end of the day. Okay, so let's look at this one. You can kind of see how they'll set it up. I'll show you how I set it up. So we have this capital F of x is x squared plus 1. So let me show you how I would set this up. So example. So differentiate. Don't like that I much either. Let me just start over. So f of x here is the square root of x squared plus 1. So usually the way I like to do it is I'll say, okay, well, my inside function is just that x squared plus 1. And then my outside function, that's what you would plug it into. So I would say this is either the square root of t or t to the 1/2 power. So then you just take the derivative of each one of those. So inside prime would be 2x, and then the outside prime would be 1/2 t to the minus 1/2. And then what you do to find the derivative is you just multiply inside prime with outside prime, and you plug inside back in for t. So t is a placeholder for the original inside variable. So my f prime of x here would be 2x times 1/2, and then change t into x squared plus 1 in parentheses to the negative 1/2. So again, this simplifies. The 2's will cancel. So we could think of this as x divided by the square root of x squared plus 1. And that would be my derivative. So remember, the negative 1/2 power, 1/2 is the square root, and then the negative means it's essentially on the bottom of the fraction. So x over the square root of x squared plus 1. So that's typically how I set it up. I think of inside variable, outside, and I take the t as a placeholder. So notice if you would plug inside in for t and the outside function, you recover the original function. That's just, I think, the way that it seems easiest in terms of writing everything down. Again, if you want to write it down more explicitly in terms of other variables, you can do that as well. So you can see how they'll set it up. They do f prime of u, and then essentially they're just plugging g of x back in and then multiplying by the derivative of g of x. So so they plug in g of x and then they multiply by g prime of x at the end, but they get to the same answer. It seems a little piecemeal to me. I kind of like doing it all at once better, but like I said, if you end up with x over the square root of x squared plus 1, and what you did is logical, that's perfectly fine by me. And then, okay, so that was how they did it with setup number 1. This is how they do it with setup number 2. We're kind of maybe using something in between, but still, the same formula really is in play in all three. But like I said, okay, so let's kind of skip through this and look at the next problem. They have a separate rule for power rule. I'm not going to do that. I just like using the chain rule, essentially. There's no need for an additional formula. So x cubed minus 1 to the 100th power. Let's do this one. So example. So differentiate g of x equals x cubed minus 1 to the 100th power. So again, I would say my inside function is that x cubed minus 1. And my outside function would just be t to the 100th power. So then I just differentiate each one like usual. So I have the inside prime is 3x squared. The outside prime is 100 times t to the 99. And then to find the derivative, you just multiply, again, inside prime by outside prime. So I have 3x squared times 100, and then turn t back into the inside. So t becomes x cubed minus 1, then parentheses, and that's raised to the 99th power. And then to simplify, we know 3x squared times 100 is just 300x squared. So I have 300x squared times x cubed minus 1 to the 99. And that's it. So as mentioned, I don't think there's a need for an additional rule with the power rule versus any other rule. The setup is exactly the same using the chain rule. Okay, let's have a look at the next example. Notice we got the same thing, 300x squared times x cubed minus 1 to the 99. Okay, so we have the cube root of v squared plus v plus 1. Remember, the cube root means the 1/3 power. So they have a of v is the cube root of v squared plus v plus 1. And we're going to be thinking of that as v squared plus v plus 1 to the 1/3 power. It makes it easier to apply the power rule when differentiating. So again, I'm going to call my inside function just the v squared plus v plus 1. And the outside function will be t to the 1/3 power. So the derivative of the inside function is 2v plus 1. The derivative of the outside function would be 1/3 t to the minus 2/3. So then when multiplying, we would have a prime of v is the inside, so 2v plus 1 in parentheses, times the outside 1/3, and then change t back into v squared plus v plus 1 to the minus 2/3. And you can rewrite that in radical notation if you want. Our 2v plus 1 would be on top of the fraction. Then on the bottom, we would have 3 times the cube root of this v squared plus v plus 1 quantity squared. So remember, when you have the negative, that's going to put it in the denominator. 2 will become the power, and the 3 on the bottom in the exponent will become the root. So looks kind of complicated, but that's it. So notice they're getting the same thing here. They just left it as the 2/3 power, so maybe that's a bit easier to look at. Typically, if they start with radical notation, I usually write my final answers in radical notation as well. I mean, that's not a requirement. In general, probably just using exponential notation all the time is the most clear. And it doesn't say this, but a lot of times in problems, they'll want you to write your final answer using only positive exponents. So that's probably why they put it in the denominator. Okay, let's have a look at this one. This is a bit complicated because we're going to use several rules here. Probably the quotient rule and the chain rule. They say power rule as well. Yeah, okay. Fair enough. So let's have a look. T minus 2 over 2t plus 1 to the 9th. Let me just change everything back to x's because I like to use t's for my placeholder variable. So x minus 2 over 2x plus 1 to the 9th. So again, the setup is going to be the same. Our inside function is x minus 2 over 2x plus 1. Our outside function is just t to the 9th. So the outside prime is relatively easy to find. That's just 9t to the 8th. But my inside prime I have to find using the quotient rule. So let's do that right here. So that would be u is x minus 2. V would be 2x plus 1. So u prime is 1. V prime is 2. So my inside prime is u prime v. So multiplying by 1 doesn't do anything. Minus uv prime, 2 times x minus 2 over v squared, 2x plus 1 quantity squared. So this comes out to, we have 2x minus 2x, that goes away, and then 1 plus 4, so we have 5 over 2x plus 1 squared. So that's our inside prime. So this is kind of just scratch work. So 5 over 2x plus 1 quantity squared. So then our whole derivative f prime of x we get by multiplying that in prime by out prime. So we have 5 over 2x plus 1 squared times 9, and then change t back into the original inside. So x minus 2 over 2x plus 1 to the 8th. So we can multiply the 5 and 9, so we get 45 over 2x plus 1 squared times, all right, so if we use the exponent rule, we have x minus 2 to the 8th over 2x plus 1 to the 8th. I'm only doing that because the bottoms both match at 2x plus 1, so you can actually combine those and write our final answer a little more cleanly as 45 times x minus 2 to the 8th over 2x plus 1 raised to the 10th. So again, you wouldn't have to do all that simplification. You could stop, probably all the way up here if you want. But I'm just trying to write it how I think the book will have it written. And that's in the final form there where they combine the denominators. Okay, let's see if they got the same thing. Of course, they'll have t's involved, but yeah, 45 times t minus 2 to the 8th over 2t plus 1 to the 10th. Exactly the same thing as what we got. They did their quotient rule all at once right here. We kind of did it on the side. I typically think that's, I don't know, I would have just rather had it done separately. Okay. So this one has a chain rule within the product rule. So let's have a look at this one. Yeah, so you have a u as a 2x plus 1 to the fifth, and then a v as a x cubed minus x plus 1 to the fourth. So when you find u prime and v prime, each one of those will have a chain rule. So let's go ahead and do this one. So differentiate. Y equals, was it 2x plus 1 to the fifth? And then x cubed minus x plus 1 to the fourth. Okay, so again, we have a product rule initially, and then each factor in the product rule is going to have a chain rule. So I would say, okay, let u be 2x plus 1 to the fifth, and let v be x cubed minus x plus 1 to the fourth. And then to figure out u prime and v prime, we're going to need to do the chain rule on each one of those. So u prime we're going to have here, v prime we're going to have here. So my u prime, I'm going to have my inside as 2x plus 1, my outside as t to the fifth. So my inside prime is 2. My outside prime would be 5t to the fourth. So then again, you multiply them. So my derivative here would be 2 times 5 times 2x plus 1 to the fourth, which would be 10 times 2x plus 1 to the fourth. So that's u prime. So that's kind of scratch work for u prime. Then v prime, we're going to do the same thing. So our inside will be x cubed minus x plus 1. Our outside will just be t to the fourth. So then our inside prime is going to be 3x squared minus 1. Our outside prime is going to be 4t cubed. So our derivative here will be 3x squared minus 1 times 4 times x cubed minus x plus 1 to the third. So I'm not going to simplify anymore. I'm just going to rewrite the 4 in front. 4 times 3x squared minus 1 times this x cubed minus x plus 1 to the third. So fairly complicated looking derivatives here. Whoops, let me undo that. Okay, so this is from this. Okay, so now we want to do the whole derivative. So y prime is the product rule, and it's going to be a big old mess, but again, I'm just multiplying diagonally. So u prime times v. So I've got 10 times this 2x plus 1 to the fourth times x cubed minus x plus 1 to the fourth plus, and then I do u times v prime. So I've got 4 times 3x squared minus 1 times x cubed minus x plus 1 to the third, and then times 2x plus 1 to the fifth. And it's a big old mess. It doesn't simplify in any nice way. I would just leave that alone as is. As I said, with these product and quotient rules, the derivatives aren't necessarily simplifying. They can just get more complicated as you go on. So as you can see, they're getting some big mess as well. They did do some factoring. They factored out the biggest term, but probably sorry, I meant to just highlight. This top line here is the one that probably looks most similar to our answer. Maybe we can do a side by side and see. So 10 is the second term here. They've got 5 times 2 still. So 10, they've got 2x plus 1 to the fourth, x cubed minus x plus 1 to the fourth as well. So the thing that we were at first, they were at second. And then the first term, we have the 4, the 2x plus 1 to the fifth, x cubed minus x plus 1 to the third, and 3x squared minus 1. So it matches perfectly with just stuff shuffled around a bit. Okay. Okay, so looking at exponential functions, again, we don't need any rules here. We can just apply the chain rule. So e to the x squared. Let's go ahead and take the derivative of that. So our inside here will be the exponent, the x squared, and our outside would just be e to the t. So notice that if you plug the inside back in for t, you get exactly what the original formula for y is. So that's what's going on. That's how we're decomposing these things. So then, again, inside prime should just be 2x, and the outside prime is just e to the t. So when we do our y prime, how do we do it? We do inside prime times outside prime, so 2x times e, but we replace the t with the original inside. So y prime is just 2x times e to the x squared. Fairly simple chain rule there. Oops. Okay. Derivative of a to the x, again, we don't need another formula for that. We can just so let's just look at this part. 3 times 5 to the x. Let's say we had to do the derivative of something like that. So differentiate. Say let's do something a little different, maybe even than that. Let's say f of x is let's say 3 to the 5x squared minus 7. So our inside function here would be the exponent 5x squared minus 7. And our outside, we would just replace that exponent by t, so that would just be 3 to the t. So then the inside prime is 10x, and the outside prime would be the natural log of 3 times 3 to the t. So that's maybe the derivative formula we encounter the least frequently, the simple one. The exponential of the form a to the x. So remember, that's just the natural log of a times a to the x. So if you forget, go ahead and look that one back up and try and remember it for next time. But once you've got the setup complete, everything's pretty easy. Our f prime of x is just going to be 10x times the natural log of 3, and then times 3, and then replace t by 5x squared minus 7. And that would be it. So nothing too difficult there. So probably this is a good stopping point for today. We've seen kind of all the different forms plugged in. So have a look at the homework questions with the rest of today's time. And if you have any questions there, we'll look at those next time and do a few more examples as well. But that's the main idea for the chain rule. We've seen quite a few examples. And there's other ones in the other chain rule video that I have. So if you haven't watched that yet, please go ahead and do so.